This is a square. We can divide it into 4 smaller squares and paint the top left corner yellow. The fraction of the square filled with yellow is equal to 1/4. Now let's divide the bottom right square into 4 even smaller squares and paint the top left one yellow. Now the fraction of the big square painted yellow is equal to 1/4 plus 1/16. Now we can again divide the bottom right square into 4 smaller squares and paint one yellow. The fraction of the square painted yellow is now equal to 21/64. Imagine that this pattern goes on forever. What fraction of the main square would then be yellow? The first yellow square is equal to 1/4 of the big square, the next yellow square is equal to 1/16, the next 1/64, and so on. This creates an infinite sequence where each term is 4 times smaller than the previous one. The fraction filled with yellow would just be equal to the sum of all the terms in the sequence. To calculate this sum, we can use this formula, where a1 is the first term and r is the ratio between terms. If we plug in the values into the formula, we get that the fraction of the main square filled with yellow is equal to 1/3. But what if I told you that we didn't have to do all those calculations and know the fraction painted yellow immediately just by looking at the square? Let's remove the bottom right square. We can see that the area painted yellow is 1/3 of the whole shape. Now let's copy this shape and put it in the bottom right corner. We added 3 small squares and one of them is yellow, so the total area of the yellow section didn't change. We do it again and again and the yellow fraction always stays 1/3. This method also works for different shapes. For example, a triangle. We divide it into 4 sections and we paint 2 of them yellow. Now we divide the small triangle in the bottom left into 4 smaller triangles and make 2 of them yellow. This pattern continues forever. If we try to look at the whole triangle without the bottom left section, we can see that 2/3 are yellow. After adding the 4th triangle, that's also painted yellow in 2/3, the area of the whole yellow part doesn't change. Now let's look at a different triangle. We divide each side into thirds. We draw new triangles on each side using the middle third as its base. Then we erase each middle third. Now we repeat the same process for the smaller triangles. Imagine that we do it infinitely many times. The shape that we get is called the Koch snowflake. Let's say that each side of the main triangle has a length of 1, so the perimeter is equal to 3. In the first iteration, we removed 3 lines of length 1/3 and added 6 of the same length, so the perimeter of the whole shape is now equal to 4. In the next iteration, we removed 12 lines of length 1/9 and added 24 sides of the same length, so the perimeter is now equal to 16/3. Between each iteration, the perimeter grows by a factor of 4/3. So after infinitely many iterations, the perimeter is infinitely long. But now let's look at the area of the Koch snowflake. For easier calculations, let's say that the area of the main triangle is equal to 1. In the first iteration, we add 3 small triangles, each having a side length of 1/3 of the big triangle. So the area of each triangle is 9 times smaller than the area of the main triangle. The area of the whole shape is now equal to 1 plus 3 times 1/9. In the next iteration, we add 12 triangles with an area of 1/9 times 1/9. So we add 12 81ths to the area of the whole shape. So after infinite iterations, the area of the whole shape is equal to 1 plus the sum of this infinite series. The ratio between elements is equal to 4/9. So after plugging in the values into the sum formula, we get that the area of the whole shape is equal to 1.6. It means that the Koch snowflake has a finite area but an infinitely long perimeter. Geometry can be quite surprising when we consider infinity. A line has only one dimension. We can bend it, but it's still just a curve and it cannot cover an area. Or can it? There are special lines called space-filling curves. One example is Hilbert's curve, and it is constructed like this. We start with this simple curve. Then we make 4 copies of this curve, arrange them like this, and connect them so they are still a single curve. Then we just repeat the same thing. We make 4 copies of the curve, arrange them like so, and connect them. Imagine that we did this infinitely many times. The length of the curve diverges to infinity, but it is contained in a finite amount of space. After infinite iterations, the Hilbert's curve goes through every point in this area. That's why it is called a space-filling curve. Now let's go back to the one-dimensional line. This line represents the interval from 0 to 1. Now we remove the middle third from the line. Then we remove 1/3 from each remaining interval. The Cantor set is the set of points that are at the ends of all intervals. After 2 iterations, there are 8 points in the set. And after every iteration, the number of points doubles. Imagine that we did this infinitely many times. Then the set of all points at the ends of the intervals is infinite. But now let's look at the length of the lines that we removed. In the first iteration, we remove an interval of length 1/3. Next we remove 2 intervals of length 1/9. Next we remove 4 lines of length 1/27, and so on. So the total length that we removed from the interval from 0 to 1 is equal to the sum of this infinite series. The ratio between elements of this series is equal to 2/3. So the sum of all terms of this series is equal to 1. It means that from the interval of length 1, we removed the total length of 1 and we still ended up with infinitely many points. The Cantor set is defined using one-dimensional line. But now let's look at the 2D square. We divide it into 9 smaller squares and remove the middle one. We repeat the same process for each of the smaller squares. We divide them into 9 smaller squares and remove the middle one. We repeat this infinitely many times. The shape that we get is called the Sierpinski carpet. In the first iteration, we removed 1/9 of the total area. In the next, we removed 8 81s, then 64 243rds, and so on. The sum of this infinite series is equal to 1, so we removed the area of 1 from the square of an area of 1, but we ended up with the shape that has infinitely long perimeter. Another shape that is created using the same method is the Sierpinski triangle. We start with an equilateral triangle, divide it into 4 smaller triangles, and remove the middle one. We repeat the same process infinitely many times. This shape is self-similar, meaning that if we zoom in on any of the small triangles, we can see a shape that looks like the whole Sierpinski triangle. What's interesting about this shape is that it appears in many different places. One way to construct it is by starting with the Pascal's triangle. To construct it, we start with 1. The next row is constructed by summing adjacent elements in the previous row. Because there is only one number in the top row, we assume that there are 2 zeros next to the 1. So the second row is 1 and 1. The next row is 1, 2, 1. Next 1, 3, 3, 1, and so on. We can continue this process infinitely many times. Now we fill every odd number with red. The shape that we end up with is the Sierpinski triangle. Another way to create this triangle is to play the chaos game. We start by placing 3 points that form the equilateral triangle. Now we place a point randomly inside the triangle. Then we randomly select one of the vertex points and place a point half the distance from the current position. And we do it again and again, each time selecting random vertex and moving halfway to it. After placing more and more points, the shape starts to look like the Sierpinski triangle. With those simple rules, the chaos game can create interesting shapes. But we can play the chaos game using different rules. For example, we can use those 4 transformations. We start with x and y both equal to 0, and randomly apply one of the 4 transformations. Each transformation has its own probability. We take the current x and y and calculate the new x and y. We place the point in the new coordinates, and we apply the random transformation to those new coordinates. We repeat this process many times. The shape that we end up with is called the Barnsley fern. We are back with the line. This line will allow us to create the dragon curve. We create a copy of this line and rotate it 90 degrees clockwise. Then we create a copy of the whole shape and rotate it again 90 degrees to the right. We repeat this many times. We copy the shape and rotate it 90 degrees clockwise.